Now let's talk about the emission control strategies. Now, as I mentioned, when the challenges comes for the legislation norms, there are two strategies, either in-cylinder strategies or after-treatment technologies. So when I say the in-cylinder strategies, is like the engine out emission norms we try to control so that you require the minimum after-treatment devices, the loading, or it can be the best performance and then it can be handled with the after-treatment technology. But as you know, after-treatment comes with the precious metals, and then the loading of those precious metal has to be minimum so that you require a minimum support of the after treatment technology, and because of the cost can be controlled. So if I talk about the diesel, it can be bowl or injection strategies, EGR, downsizing, downspeeding, component design optimization, and many more. And after treatment, we can have SCR, DPF, DOC, or in for gasoline, it can be three-way catalytic converter. So based on now, if you see this current scenario in Euro 6, how industries, if you see now different OEMs, they have handled these approaches different ways. So there can be two options to handle the NOx, SCR versus EGR strategy. There can be selective catalytic reduction or there can be exhaust gas reduction. Now there are some few companies which has not used EGR at all. So there is no EGR, but still they have achieved the Euro 6 norms with the help of the SCR. And there are few companies who have used the combination of EGR and SCR. So moderate level of EGR to high level of EGR and then SCR. But you won't find a single company which has used only EGR. There's no single company because it's not easy to achieve those emission norms only with EGR. The durability problem comes with the EGR. So there are, you will see the products with only SCR, this Euro 6, and there are combination with the EGR and SCR. Now you must be knowing that EGR and SCR, they are used to control the NOx. The problem with only SCR is that when you go with the only SCR, the urea consumption goes on higher side. But there can be a marketing strategy for only SCR, like when you go with the only SCR, obviously the durability improves and then the oil interval improves because of that. The fuel mileage also improves because of that. So there can be different strategies based on their customer requirement, their where their maximum sale in the particular country, which zone, accordingly they can have the strategies, and then there can be combination of EGR, SCR, or only SCR plus EGR. So let's talk about this engineering targets now. So as engineers, when we work in any industry, always we have to work with deadlines and the targets. But when you say the deadlines and target, it is not that simple that you just change one parameter and you get the required target. It's always there are constraints. So just if I take the engine as an example, the targets can be performance and emissions, but the constraints, always the constraints are mechanical limits. Let's say in cylinder pressure, you have less limit of 200 bar, you cannot go above 200 bar. Or after treatment conversion efficiencies, let's say 97, 98% of conversion efficiencies you can get. And obviously the cost. We cannot just use some material which is not feasible to manufacture. And there are always trade-off between so many parameters simultaneously. There is always trade-off between NOx and BSFC. There is always trade-off between NOx and PM. There is always trade-off between the particular number for GDI case. So when you say the trade-off, what do you mean by trade-off? Just take example of BSFC versus NOx. Now, if I plot this BSFC versus NOx, what I see that if I try to minimize the NOx value, what is happening to the BSFC? It goes on higher side. And if I try to minimize the BSFC, what is happening to the NOx? It is going on the higher side. So always there is a trade-off between the BSFC and NOx, and there is not a single solution available, but there are multiple solutions available. So depending on our strategies, we can decide which combination we should use. So let's take about, obviously there are always constraints with this exhaust temperatures. It cannot go less. In case of diesel, it cannot go above 700 degree, or in worst case 720, 730 degrees centigrade. In SI engine, let's say 900, 1000 degrees centigrade. in-cylinder pressures, as I mentioned, then airflow ratios also. Airflow ratios, there in diesel engine, obviously in gasoline, we always try to maintain lambda equal to 1, but when let's say it's diesel, we ensure that it is not going below 18 or 19 airflow ratios. So all those constraints also we have to say. Now let's see what do you mean by calibration as such. So let's take this example of one engine where there is a torque versus engine speed, and this is a torque point. So this is called a full load curve, or when the acceleration pedal is 100%. This is what the curve I get. So depending on the application, this speed varies. Let's say if it is a passenger car application, diesel application, the speed maximum speed goes up to 5,000, 6,000 RPM. If it is gasoline, then goes up to 7,000, 8,000 RPM. If it is heavy duty application, this speed goes up to 2,500 RPM. Or if it is a tractor application, the speed goes up to 2,000 RPM. And depending on the engine size, the torque will vary. So this is what the engine operating zone, and then there can be 100% operations, 75, 50, or in between this. So this below this entire zone is called a part throttle performance, or PTP points, where the engine actually operates. So there can be target for an engineer to BSFC and NOx, in-cylinder pressures, exhaust temperature. There can be different parameters. So let's take example of diesel passenger car. The very parameters can be rail pressure, start of injection, duration of injection, pilot quantity, EGR quantity, etc., etc., etc. There can be n number of parameters. So imagine my engine is operating at this point 100%, and how it operates in ECU. That ECU gets the signal from the driver, the acceleration pedal. Based on the acceleration pedal and engine speed, there all the maps are there. So first it will start with the inner torque, that how much inner torque it should generate. Then to generate that inner torque, how much fueling should go. Then for that fueling and that particular speed, what should be the rail pressure, what should be the start of injection, what should be the fuel, pilot quantity, what should be the EGR wall position, what should be the turbine, if there is a variable geometry turbine. So like n number of parameters. And now as a calibration engineer, they have to come up with the single set of input for each combination, or nothing but the map of that particular parameter. Now how it is done? So obviously tradition, as I mentioned, traditional method is like take this, build the engine, take it on the dyno and test this all those parameters and come up with the single set of input. And obviously there can be statistical methods, optimization, we can use genetic algorithm, we can use some optimization techniques to come up with those combinations. Now if now imagine if I, instead of the physical engine, if I have the virtual engine where I can my mathematical model behaves like a physical engine, and now I can use some simulation tools such as GT Power, where I can model the complete engine, after treatment, DOC, DPM, SCR, and then I can come up come up with the calibration strategies, and then I can come up with the set of all those inputs that what should be, and then I will hand it over these values to the test engineer, and then test engineer will do. So that is something called a virtual calibration, and this is what now commonly used in the industry to calibrate the engine, because as I mentioned, the parameters are increasing, the number of parameters, because imagine this is limited to only when the lab conditions. What will happen when on the road more parameters are added, right? Now let's say driver, the how the he's changing the acceleration pedal. There can be aggressive driver, there can be moderate driver, or let's say this traffic conditions, or there can be a variation like the road surface, the gradient, so many variabilities. So all those I cannot just consider on the test bed, and then virtual calibration is the right methodology for that. Now after this, I'm just coming back to hybrid. Now a lot of people are asking about what is a hybrid configuration. So now base hybrid is nothing but the combination of the electric vehicle and IC engine. So there can be a pure electric vehicle somewhere here, or there can be pure IC engine, or based on the hybrid level, we can have the micro level, mild level, medium level, full level, or plug-in hybrid. So there can be different combinations of hybrid depending on the application, as I mentioned. So just to give example, there can be 48-volt hybrid system, where 48 volt hybrid system, we can have electric turbocharger, or we can have the electric water pump. Now, what is the advantage of going with the electric turbo and electric water pump? Because now no more they are depending on the engine speed now. So I can just adjust the requirement of water flow by just changing the giving the input to the electric motor or in electric turbo. So that's the main problem with the passenger car, that when there is a city operation, they get the turbo lag. So this can be reduced with the electric turbo. So there can be different combinations of hybrid. And then when you are adding the hybrid configuration, obviously you are adding more parameters to that. So now there's a battery management system, the state of charge, uh, motor. So all those parameters need to be handled. So which can easily handle with the GT power or as such simulation tool. Now there's something called efficiency versus temperature for after treatment devices. Now after treatment devices, there's something called a light off. So where the minimum temperature is required for the conversion efficiencies. So there's a light off temperature for DOC, SCR. There's a light off temperature for three-way catcon. And then you have to ensure that the temperature when it enters, when the exhaust enters into the after treatment device, you have to ensure that there is some minimum temperature so that we get the efficiency conversion, or we get the proper conversion of those pollutants. It's very, very important. And this point limits so many and this is very challenging for the calibration engineer as such, because they cannot just like that do the combination by ignoring those turbine outlet temperatures. So let's talk about this after treatment in the diesel engine. So there's the engine out, then there's the DOC, DPF, SCR. So what are those emission norms? CO, HC, NO plus NO2, PM and PN. The DOC is diesel oxycat, which takes care of CO and HC, and also it converts some part of NO into NO2. Now, why this? It converts NO into NO2 because NO-NO2 ratio, if it is 50%, I get the highest conversion efficiencies in the SCR. So DOC plays that role. DPF, obviously, it takes out particulate matter and it reduces the particulate number as well. And then it goes to the SCR, NO plus NO2. And then finally from the SCR, everything is reduced. So finally what we get at the tailpipe is pure air plus some part of CO, HC, NO, NO2, PM and PN, which is allowed within those legislation limits. Now, as I mentioned, all these legislation norms are pushing the boundaries of all those engine design and everything. The existing engines, they cannot survive those future emission legislations, and therefore there is a basic change which is happening in all those engine designs. So one of that example people are working is the cylinder deactivation. So there can be, let's say at the part load condition where I don't require 6 cylinders to operate, I can operate only with the 3 cylinders. But the problem here is the balancing of the engine. But you see that there are so many commercial products available nowadays with the cylinder deactivation technologies. One of the example is from the Ford. Now here I would like to highlight, this is a case of this Paris, and they have, I read one paper where they give some example that, so there's the three, you will see the three lines here. One is the red, yellow, and this is the third line. So red is that no LEZ baseline scenario, LEZ is the worst scenario, and third is the LEZ best scenario. So these are the three combinations which are there. Now if you see here, the on x-axis this is the year, and on y-axis passenger car fleet's average NOx emission factor mg per kilometer. So what they want to show here is that how quickly they can reduce those emission norms to, let's say, from existing level to less 84% less. So let's see, if they want to achieve this as early as possible, let's say by 2024, what they have to take. Let's say now this is the current year, let's say 2018-19 when they happen. What they are telling is that Euro 3 diesels are replaced with the Euro 6D10 petrol cars. Then next scenario is that in the year 2022, Euro 3 petrol and Euro 4 diesels are replaced with Euro 6D petrol cars. And last scenario is Euro 4 petrol and Euro 5 6D diesel are replaced with the Euro 6D petrol cars. So if they do this kind of strategies, they can reduce those NOx emissions to 84%. Or let's say they want to reduce it to by 76%, what they have to do is Euro 3 diesels are replaced with the Euro 4 diesels. So diesels are replaced by diesels here in this scenario, and in this scenario diesels are replaced with the petrol cars. So if you see, there is a addition of 8% benefit because of that. But obviously diesel cars are known for their best efficiencies, so this scenario can be possible in one particular city but obviously not on highways. And this is why I'm telling this is because you will read this such articles in news in magazines that okay, there's a ban, complete ban on the engines, but it is partly true. There cannot be a complete ban on the one particular technology. That's what industry is forcing that to the governments, that they cannot push one particular technology. They have to set the limits, that this is your targets, and then let industry decide or let the customer decide. Let it be customer driven. It cannot be forcefully. So that's what they're telling, that as I mentioned, definitely existing engines will not continue, but they will come up with the new technologies such as cylinder deactivation, 48-volt hybrid system, or there can be advanced combustion concept. So a lot of things are happening around. So this is one example where I wanted to highlight. One is this system S1, S2 and S3. So this is the one paper which I read, and this is the scenario they are telling, that in the year 2027, when there is a further reduction of 90%, all those emission norms from the Euro 6 level. So if there is a further reduction of 90%, how they can handle, how they can industry can tackle. So this is the current system one. This is system two now. What we can see here is that there's one more addition of SCR here, and there's a two addition of UAR dosing at level 1 and level 2. And there can be system 3, that there is a SCR immediately after the turbine, and then there's a DOC, DPF and SCR. So this is the normal system. So same as the S1, but only addition of the low SCR. So with they are telling that with the existing technology itself, they can achieve those emission norms. So that way, this technology is robust. And if the industry can tackle this uh, problem with a very robust calibration support, definitely the existing technology of the after treatment or existing IC engine with some more electrification or with some advanced combustion, they can continue and they can achieve the future emission norms. Now the question here is that why the perspective of the people is changing. People are feeling that IC engines are bad, electric vehicles are zero pollution, but that is not the case. Electric vehicles, if you consider the well-to-wheel combustion, well-to-wheel efficiencies, all are comparable or at some countries. So that is a country specific, because how electricity is produced in that particular country. And now the second point is this particulate numbers. Now this tire wear. So tire is also the major contribution of the particulate number, this tire or brake wear or clutch wear. So that will remain with the electric vehicle as well. So all those, considering all those scenarios, you will see that there's a two experts who will be either taking the side of the IC engine or taking the side of the electric vehicle. But some I would say that as a mechanical engineer or maybe some engineering background, or I don't know, automotive engineering background, if you are really interested in working this automation, I think we can take a approach in between. We can take the hybrid approach definitely. So we will give more focus on the hybrid technologies, so that the best of these two we can definitely learn. So that's what my suggestion. So with this, what I want to just conclude is that there is no one size fits all solution. Hybrid vehicles are most practical and affordable way to immediately reduce the emission norms, and that's what the experts are telling. OEMs will definitely continue to invest in IC engine technologies to explore untapped potentials. Just to give example, it is Mazda Skyactiv, which blends the combination of diesel and gasoline engines.